So far we have seen how to use PyTorch's auto differentiation feature to find the minimum of a function, and for that we have a function here, y equals x minus 3 to the square, and we have a variable that we want to differentiate against, which is x, and this requires grad. So when we call y backward, we compute the gradient of the function y at the position x, and then we had this step where we use no-grad enabled update the function x by adding a piece of the gradient to it to move against its direction, and then we zeroed the gradient manually. Now there's a better way to do this, which is to use PyTorch's built-in optimization routines, which do these steps for you. And the advantage is that you will be able to use a lot of other features of the PyTorch framework, including different optimizers and things like momentum terms or batch processing. So let's look at how this actually looked like. When we run this for 10 steps, we get pretty close to the optimum, and the gradient is almost 0. Now, in order to use the PyTorch optimizer, we take the code from here and we add a line to it, which is initializing the optimizer itself, and we have to do this after we define the variable. So we do something like this. In this case, we are using the built-in optimizers from Torch, and we use one which is called stochastic gradient descent. And here we provide a list of all of the variables that we are actually optimizing for. So the optimizer can do the update step for us, and we are providing the learning rate. So now with this, we can go here and change this and say we don't do this manually anymore with this learning rate and computing the gradient manually, but we can just simply say optimizer.step, and then we say optimizer 0 grad, which is resetting the gradients to 0. So let's run this and see what happens, and you will see it is exactly the same outcome as before, because stochastic gradient descent really doesn't do anything else than what we have been implementing manually. Again, why would you do this? I have now this opaque step here. I don't really know what's happening inside. I'm telling you today that this is what happens here. And then we have the 0 stepping, but now we can very easily leverage some other features of the algorithm. All right, before we move on, we should look at a little more complicated problem, which is a little more aligned with what we will do in this class, which is actually optimizing large batches of inference problems. And in this case, we will start with a random data set where we have 1,000 points that we want to classify. So let's start with some kind of manual seed, and we will use the answer to the universe, 42. So before we continue, we will use a little more complicated data set, which is actually not just function optimization, but an inference problem. And let's build something really simple here. We want to use a manual seed that makes it reproducible on your computer. We get 1,000 pairs of numbers. So in this case, we get 1,000 tuples here, and now we want to label them somehow. And one simple way of doing this, completely random of course, is to just add up the first and the second component, and if those two are larger than 0, we want to call this true, and otherwise we want to call it false. Now this doesn't work. In learning we need floating point numbers, so we can have something like this. Let's see how this looks like. And you see now we have a floating point number. Let's remove this real quick so you see that. And we have true false values. So we get float. Now one of the problems we have is the shape of this is now 1000 by 2, and the labels is only a shape of, well, 1000. It doesn't has a second dimension, so you see that here. So the other dimension lacks, and in machine learning this is very often, or in Torch this is very often a problem, and you have to have all of the things to have the same dimensionality. And as previously we unsqueeze it, now our shape here is 1000 by 1, and this is actually not what we want. We want to unsqueeze the other dimension, and so we get something like this, which we can then use directly with our input. What we also want to do is we want to create a very, very basic neural network. Let's say this is really just very linearly separable problem, and we can do this with just 2 neurons. So we use zeros, and we have 2 neurons here, and this of course requires grad to be true because we want to optimize these values. So these weights won't be 0 once we are done, and we also have a bias term for each of the neurons. All right, so with that we can continue writing our code. We don't have, 2 things are missing still, which is a sigmoid activation function, which makes sure that the output of the network is actually stuck between 0 and 1. We can do this manually here real quick. So this is the sigmoid function. We return 1 over 1 plus the exponent of minus c, and if you want we can visualize this real quick just to make sure we are doing the right thing here. And Gemini will do this, visualize, and we are getting that. And so here's our sigmoid function. You see it is never going below 0, it's never going above 1. It's exactly what we want our network to do. Let's remove this here, we don't really need this, but we also need a cost function. So normally we use the binary cross entropy, and we will talk more about this stuff later in the class. For now we are just going with a very basic implementation. So you provide the prediction and the true values, and then you compute the negative log likelihood. And this is already something that Colab wants to do. There's only one little thing that I would change here, which is I would add some terms like these, so that this will never become 0, because log of 0 is negative infinity, and this is something we don't want. And it might be that the prediction values are actually going down to 0, so this will improve a little bit numerical stability. All right, so with this I'm happy. What's missing here? Something. We want to close the parenthesis, and now we have some loss function, and let's see what happens when we run this with our So we get zeros all across the board. So this would be the optimal loss. We are predicting essentially exactly what we are putting in. All right. So in order to complete the neural network, we need two lines. The first one is we compute the predictions from the neural network. And so in this case, this is not what we want. We want the sigmoid activation of the input x with multiplied with our weights and adding the biases term. And here's already where you see why this dimensionality matters. If you would have done this any other way, then this matrix multiplication wouldn't have worked, and so wouldn't have adding the bias term. Now the last step is to compute the loss, and that is the binary cross entropy between the prediction and the true values. We can actually do this right now and see what happens, and see what happens when we have zero weights. And so maybe here we have, well, non-trivial weights, non-trivial losses. They're all very small, but summed up, this would be quite a big number, because obviously there's no point we can get this right. Let's visualize this real quick so we're all on the same page on how this data look like. Please visualize this data set, and let's see if it comes up with something meaningful by itself. And so what we expect is essentially scatter plot of true and false values. And you see here we said as soon as the sum of these two is larger than 0, we want it to be in the class 1, and otherwise want to be in the class 0. And so optimizing this should just get us a line that separates these things at exactly that demarcation line. So we should get the loss down to very little once we train this. Now the point of this is to show you how to use the Torch optimization framework from scratch to train these things, and how to use optimizers. And we have talked about this with the simple function minimization, and we want to do this now for this example. So let's start. We set the learning rate to be somehow 0.1, and we present the data set, let's say 20 times, and now we run our prediction step, we compute our loss, we compute the gradients with respect to our weights and biases, and as you remember, it is really simple. We just say loss backward, that does all of this. Now we have to update our parameters, and let's do this manually real quick so you see really the advantage of using the optimizer in this example. So in this case, we want to update the weights and move by the learning rate against the gradient of it. So this comes from computing loss backward. We have the bias term, and we change that again with the learning rate and bias.grad. And now we have to zero the gradients. Weights is grad 0, and bias is grad.0 as well. Now all we need to do is we have to print the result every epoch. Let's see if this goes automatically. No, it doesn't want to help me yet. Oh, epoch, and then we don't want to start at 0. Let's print this nicer and say the loss is the loss, the actual value, not the. And this is actually something worth knowing. When I print the loss, I print a tensor, so I get all this information from Torch, which I don't want. So using the method item is actually extracting the actual value, and so this should do a good job printing. Let's run this, and something is wrong. So this is an interesting problem, and the reason lies in the way here the loss is computed. And I should have noticed this earlier. The loss should be the sum of all of these. And so what we've done wrong here is we forgot, or I forgot, to actually sum all of these things up by the mean value. So this should work now. And you see the loss is not changing at all so far. And this is probably because I did run this before, so I should make sure I reinitialize all of these things when I want to test this. Okay, so now last time running this, and we should get a relearning experience here. Loss is going down from 69 to 48. That surely is not the end of it. Let's do this a little more and present the data set, let's say 100 times. And we are getting down to 0.28. I don't think that is the end of it. Let's see what happens after presenting it 1,000 times. And we are getting down to 0.11, and it doesn't seem to change too much from here on out. So let's keep that in mind, that our loss is 0.1. I don't want to see too much of this, so let's do it that way. All right. So we can now do this with the optimizer, and the way this works is we define our optimizer after we are defining all the variables. And so in this case, we can do this here, and we say optimizer equals torch optim, and then we grab the SGD optimizer, and here it already recognizes, oh, this guy wants to do this with the weights and the biases. And we then have to finally provide the learning rate, which I set to be 0.1. Now you might see that the optimizer is really cool because I don't have to do all of these manual steps here. I can just say optimizer step, and it will do that, what you just seen here. And then I have to say optimizer 0 grad, and it will take care of the gradients. So let's see if this changes anything. It doesn't. It's the exact same outcome, and we can now go from here and see what else we can add. So one of the things that you will always do in machine learning is you will never, or almost never, present this entire data set as we've done here. So these are the 1,000 samples that we had, but you will break this somehow into mini batches. And so one way of doing this is to use a torch function called runPerm. And so I can show you that here. If you do runPerm, let's say of 10, you will get numbers from 1 to 10, but in some kind of random order. So you see, this is a random permutation of the numbers 1 to 10. So I can do this over and over again. So if I do this for x.size 0, I will get the numbers to index my data set. And I don't want to show this here because too many numbers. And I can do this actually in every epoch. So the first thing I do is I say, I don't want to do this all at once, but I want to do this in little mini batches, and for that I first get some random permutation and I shuffle my data set. So I call this x shuffled and y shuffled, and this is very simply just the data x with using this random permuted index. So that's already in here. All right. So now I have a shuffled data set, and now I can go and say, okay, instead of doing this all at once, I want to do a mini batch. And so I could do like this way. I could go from 0 to, and already sees what I wanted to do. Yeah, so it goes from 0 to the length of the vector, which is 1,000, and it does this in steps of 100. So each of the batches has size 100, and now I can grab my batch. Is this actually, yeah, that is a good, but here I also need to add I plus 100. plus 100. And so what this will do is I is going in these huge steps from 0 to 1,000 in steps of 100. So we are going to get the first 0 to 100, and then we get the next, and so on. Now let's make sure this is not right. That should work. I grab it from here, and now I should do all of this not on my full data set, but actually just on my batch. All right. And here I use the Y batch. So I think this should do it. I computed the loss based on Y prediction and the Y batch. I compute the loss backward. And so here I'm now doing this. I'm computing the gradient only for these 100 samples of my overall 1,000. So let's see what happens when I run my epoch. And I don't expect, so here we are after 10 epochs, we are at 57. Let's see what happens when I do it that way. And we are actually getting down a lot lower. And this is interesting because we haven't changed much, but actually changed the presentation order of how the values are presented. So before, when we ran 10 epochs, we presented 1,000 at once and computed the average gradient over all of these. Here we have done this broken down into 10 substeps, and so essentially we do not just 10 but 100 gradient updates. So by doing that, we are actually getting faster and better results. All right, so this is great. The optimizer helps us to do this in a manageable way without like keeping track of all of the gradients and all of the variables ourselves. But there's more that we can do. Another feature of the optimizers in PyTorch is the very simple addition of, let's say, momentum. Actually, this is a feature of stochastic gradient descent. So to make it a little more fancy, we can add a momentum term. And what this does is it uses the previous gradient from the last optimization step and adds a fraction of it to the current gradient. So that means when your gradient is going down quickly, you have some kind of momentum in it. Let's see what this does. Now we are at 26, and sometimes it doesn't help. So actually here it helped quite tremendously. I'm going down from to 0.09. This is actually the best result we had so far. So yeah, we are reinitializing everything here, so this is actually pretty reliable. All right, so momentum is not all. There's yet one more thing that you should know about as a basic feature of the PyTorch framework, and this is you can schedule the learning rate. So in this case, the learning rate has been always constant. By the way, I can remove this here. It's not used because I'm using it in the optimizer definition here, so to avoid confusion. So what you can do is you can have PyTorch schedule the learning rate for you to change. And for example, one of the very intuitive ways of scheduling is to say, in the beginning, I want to have a very high learning rate, and then I want to drop it down quickly as I approach my goal, because I know shorter around the goal or closer to the goal, the learning doesn't have to, or the variables shouldn't change so much anymore. So the way to do this, I create a scheduler, and this is in the Torch Optim package. There is another one which is called Learning Rate Scheduler. And so here I can, you see it recommends all sorts of, you see what it all has. But let's just do something very simple, which is step the learning rate. And so here you provide the optimizer because it wants access to that object, so it can change the learning rate parameter. But here we say, let's say step size every 5 steps. We want to change it by gamma to be 0.5%. 50%. 0.5 is 50%. So now we have our scheduler, but it won't change anything because it doesn't yet update. So we have to go in here and actually tell the scheduler to step, and we do this, we can do this here and call step, so that will call it every epoch. And what we could do is we could maybe print the learning rate here as well. LR equals optimizer well, let's not do that. Let's do that in a second. Let's just see what happens first, if this even helps. And in this case, the learning rate hasn't really changed. So let's plot this real quick. This is non-trivial because it's a little bit hidden. So you can get it from the optimizer, and then there's something called param groups. And here we can grab a field called LR, and this is working for this optimizer. Hopefully, let's see what it does. And so you see now that every 5 steps the learning rate drops. Well, with this we have seen how to use the PyTorch built-in optimizers, how it makes code more manageable, but then also how we can throw in other things like momentum terms, or which is a feature of the SGD optimizer, or a scheduler which can schedule some of the parameters of your optimizers.